Hi, my name is Juan, and I'm a PhD student at Dalhousie University, and I am presenting unsupervised document summarization using pre-trained sentence embeddings and graph centrality, and this is the proposed method that we submitted to the LongSumm shared task inside SDP 2021. So here we have the pipeline of the proposed method. First, we take the whole document, excluding the abstract, and we tokenize it by sentences using a regular expression instead of more complex approaches, because we saw that they often fail because of how abbreviations appear in scientific documents. Then we compute for every sentence an embedding using SBERT, which is a variation of BERT specifically meant to compute sentence embeddings that can be compared using cosine similarity. And the version that we used was the base Roberta, fine-tuned on the MS Marco dataset for information retrieval. And after that, we create a graph where the nodes are the sentences in the document, and the edges are weighted by the distance between the nodes, and this is a complete graph. And after that, we compute a ranking for each one of these nodes, and in this ranking, lower scores mean more important sentences to include in the summary. And as a final step, we concatenate these ranked sentences in order. And it's important to know that since we produce a ranking for every sentence, we can essentially summarize any document of any size, and we can also satisfy any length constraint for the final summary, in this case 600 for the shared task. And after all these steps, we obtain the final summary. So how do we exactly compute this sentence graph? It's pretty simple. We, in this case, are trying to compute the ranking for this sentence S1. And what we simply do is we compare it pairwise with one of its neighbors. And the weight for the edges is simply 1 minus the cosine similarity of the corresponding SBERT embeddings. So here we have the formal definitions: cosine similarity, the weight of the edges, and the ranking is simply the sum over the rows or the columns, if you want, of this matrix here. And we can see that this matrix has a diagonal composed exclusively of zeros. It's also symmetric because the cosine similarity is symmetric, and it's also non-negative because cosine similarity lies between -1 and 1. So here we can see that this matrix can be interpreted as the adjacency matrix of a simple complete graph. And we can see also that the definition of the ranking, it's very similar to the definition of degree centrality. We are simply adding something over the neighbors of a given node. So this is the ranking. It's pretty simple. We are not fine-tuning or training any model. And here we can see the experimental results for the method. In blue, we have RUCH1, in red, we have RUCH2, and in green, we have RUCH-L. Solid means RUCH F measure, and dashed means recall. And in the bottom, we have the bottom percentage of sentences in the document. So here we are taking the bottom 1% and bottom 15%, and here we have the value of RUCH. And we can see that the best method obtained a RUCH1 of 0.46 using 10% of the sentences in the document, but these results were fairly close to the bottom 5% and bottom 15%. And we can also see that overall the recall was much lower than the F measure, implying that the precision is the one that is higher here. And after bottom 15%, the summaries are way too long, surpassing the 600 word constraint. So these are all the experimental results we have. And now we come to the conclusions and future work. So this proposed method displays competitive performance with more complex methods. To give you a reference, the best method we submitted has 0.46 compared to 0.53 of the best performing method in the task. But it's important to know that this method is very fast, very efficient, because we can use simply linear algebra libraries like NumPy. And it's also very simple to implement, and we don't have to train anything. And like I said before, the recall of the method has much room for improvement. We think that having the whole sentences as minimal text units means that it's hard to identify relevant phrases inside sentences that are not so relevant. And as a future direction of research, we think that the redundancy of method is an interesting direction for future research. And this is important because in long documents such as scientific papers, it may be that we have several versions of the same sentence that are different wording or small difference that the method is identifying all of them as relevant. So that's why the precision is high. But then that takes room for other less relevant sentences that I might have provided more coverage. So this is all I got. Thank you so much for listening. This is my email, juan.ramirez@dal.ca. And you can try a minimal web version of this project, which is a direct consequence of the method being so simple and so fast as this Heroku app. And thank you so much for listening.